Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the 13th chapter of microwave engineering, where we have the microwave measurements to be understood here. The various parameters can be measured with respect to the propagation of the microwave signal after it has been generated by the source and carried through various microwave components into the microwave test bench. We started to see how the measurement techniques at the microwave range are different as compared to the low frequency measurements. We have been introduced to the very important devices or the components, we can say, with which the measurements are made possible. So these are the slotted line and the tunable detector. In the previous videos, we have covered the VSWR measurement techniques, VSWR standing for the voltage standing wave ratio, and we have selected 4 problems solved onto it. Now let us have one more parameter that is very important as far as the microwave signal propagation in the microwave system is concerned, that it is power measurement. So let us begin with the topic. So here we start with our topic. The topic is titled power measurement. As we know, most possibly when we have the flow of energy through the wired medium, we have the measurements in terms of the voltage and the current. The multiplication of the two is in turn associated to the power, which is a measurement of energy, I can say, for the periodic type of the signal in general. So the power is measured in terms of watts here. Now when we have the energy propagation in terms of wireless medium, so that time we have, instead of voltage and current, to be the electric field intensity E and magnetic field intensity H here. So it is also giving us the measurement of power with respect to the Poynting theorem we have gone through to understand the propagation of power for a microwave signal here. Now here the microwave signal is inside a bounded medium, so we consider it is running through a waveguide here. So the power measurement inside the microwave transmission line, for example the rectangular waveguide, is having invariant with respect to the position of the measurement inside the rectangular waveguide here. Now based upon the magnitude of this particular power, we have the different techniques to be used for the measurement purpose. So for example, if we have the power measurement up to, we can have from 0.01 milliwatts up to 10 milliwatts. So for this range, we call the power measurement to be measurement of low power. And for the measurement of the low power, the technique used is of bolometer here. So bolometer is a device with which we can have the low power measurement made possible here. So bolometer technique. If we have the power of the range greater than 10 milliwatts, so from 10 milliwatts up to 1 watt if you take, so we can call such type of power measurement to be of medium power. So I write here measurement of medium power. And for the measurement of medium power, we have here the calorimetric technique used. And when we have the power so greater than the 10 watts here, so the power is simply represented by capital P when it is greater than 10 watts, so that time we can call it to be measurement of high power. And for the measurement of high power, again the arrangement is associated with the calorimetric type, but the technique is called as calorimetric wattmeter here. So one by one we shall be addressing the measurement of low power, medium power and measurement of high power. So let us first of all have a focus on measurement of low power. So for the measurement of low power, we have already stated that there it is the use of bolometer. The bolometer, or we can also take the case of thermocouples. So bolometer, thermocouples, these are the devices which are sensitive to the temperature here. So temperature, we know the temperature can be measured in terms of calories, in terms of Fahrenheit here. So the materials that are sensitive to the temperature are used in the manufacturing of the bolometer and the thermocouples, and those can be used for the low power measurement, the range as indicated. So now when we talk about the bolometer, the details can be given that the bolometers are of the two types here. So here the bolometer can be classified as barometers and that of the thermistors here. So at the low power measurement, we can have the propagation of the micro signal in terms of the voltage and the current here. So the voltage and the current, so by the Ohm's law, they are given as V is equal to IR here. So R, the resistance value, is the ratio of voltage to its current here. So whether the value of resistance is obtained to be of positive type or negative type, so this criteria differentiates the bolometer into the two types, barometers and the thermistors here. So let us see the difference between the barometers and the thermistors with the help of the schematic graph. So the first type of the bolometer that we have called to be the barometer. So in this graph we have plotted temperature values onto the horizontal axis, whereas onto the vertical axis we have plotted the resistance value. So the resistance values we have obtained as a ratio for voltage to that of the current here. So V is equal to IR from the Ohm's law. So here we see here, if we have the increase into the resistance value corresponding to the increase into the temperature values, so that time we get this kind of curvature. So there it is, rise into the temperature as well as with respect to the resistance value. So this type of the resistance can be called as a positive coefficient here. So for the positive coefficient of the resistance values when obtained for the bolometer, we call the device to be the barometer. And for the barometer here, in general, the observation is that we have 5 ohms per milliwatt here. So this is the value of the resistance with respect to the milliwatt power here. On the another hand, if we again plot the temperature values versus the resistance values, but with increase into the temperature we get decrease into the resistance. So we come to know that the resistance and temperature are inversely proportional, and the drop down type of the curvature we obtain for this particular plot, which is said to have the negative coefficient here. So the negative coefficient for the resistance curvature when it is obtained, which is the ratio of voltage to its current here, so that time the bolometer type is said to be a thermistor here. So thermistor here it is represented for the 60 ohms per unit milliwatts of the power here. So these are both the types, those are sensitive to the temperature value and they are collectively called as bolometer. The subtypes barometer and the thermistor here. So bolometer in general is a square law device as shown in the previous graphs. So from the previous curvatures you can see the square law there. So now such a bolometer represented in this capsule shape with the resistive type, hence this particular denotion in this particular symbol has been inside the waveguide cavity here. So this is the opening of the rectangular waveguide here. The broader dimension small a and the smaller dimension small b can be represented here, and inside the cavity with the help of the slotted line we can have the insertion of such a bolometer, which can be used for low microwave power measurements here. Now by having the introduction of the bolometer, we can note down the change into the resistance value with the changes corresponding to the temperature here. So here for example we see here the resistance change from R1 to that of the R2 measured in terms of the ohms. So this change of resistance will be helpful for measurement of the power here. So whatever the bolometer we have connected in the previous schematic diagram, that it was inside the rectangular waveguide cavity there. So now such a change into the resistance value, so this can be connected into a bridge here. So the bridge is supposed to be a balanced bolometer bridge here, hence the schematic diagram I name balanced bolometer bridge here. So along with the unknown resistance change, we have some known values also, R1, R2, R3, we have the R4 here, the connection with the galvanometer which is giving us the information with respect to the flow of the current, and that will be having the reading corresponding to make this bolometer bridge to be the balanced one here. We have the R5, R7, R6 also there, along with the milliampere ammeter here and the variable supply here. So as in the low power measurement, we work with the bolometer which is sensitive to the temperature here. So subject to the various conditions here, there can be the changes with respect to the measurement of the power here. So this method we cannot say to be 100% accurate, there it is a chance of errors here. Now another way to have the limitation of this particular type, that is called as low power measurement. So power handling capacity is low here, so that can be enhanced by the use of directional coupler along with the bolometer here. So in this schematic diagram, the structure that we see here, this is the directional coupler as we have covered it into the previous chapter. Directional coupler is a 4-port device. So it has the primary and the secondary waveguides. So port 1, 2, 3 and 4 here we have. Now you can see here the microwave power is given as input to this particular port, whereas the opposite port has been terminated with the match load here. Now here the two branches are for the another waveguide, a part of directional coupler here, where we have one of the port that has been closed with the help of the match load represented, whereas this port has been the bolometer element connected here, which is a part of bridge here as shown into the previous schematic diagram here. Now in between the waveguides, the primary and the secondary, we can say here we have the coupling at this particular point, and towards the port from the input port we have the coupling, we have the use of calibrated type of the attenuator here. So this is the representation here, and with this type of the measurement of the power, if we are using the directional coupler of the 20 decibels here and the calibrated attenuator of the 10 decibels here, so the total power measurement bolometer technique will be of the 30 decibels, and the 30 decibels can be giving us the power handling capacity enhanced to 1000 times than the before here, if it would be the individual measurement type here. So with this technique we can have the enhancement of the power handling technique, but still there it is as the sensitivity to the temperature, so we can have the erroneous measurement subject to the various conditions here. Now as the low power measurement has been discussed so far, there it is the medium power measurement. So for medium power measurement we have the power that is ranging from 10 milliwatts to the top the 10 watts, we can say. Basically 10 milliwatts to 1 watt is also taken, 10 watts we can also extend to. Now as mentioned before, for the measurement of the medium type of the power we have the use of calorimetric technique here. So in this particular calorimetric technique, as we know, calorie is the measurement of the temperature. Again the temperature sensitivity is there, but instead of using the bolometer, the barameter and the thermistor having the positive resistance slope and that of the negative resistance slope, here we use a specific load here, the load represented by this particular block here, which has the inlet temperature to monitor as well as the outlet temperature monitor, and to this particular load here, the specific microwave power is fed as input here. So before the microwave power has been applied to the specific load, we have the temperature first of all measured. Let us say it can be the temperature reading T1, and after it has been applied to the load at the outlet, the temperature reading can be T2 here. So the difference of the two, T1 minus T2, can finally be helpful to have the measurement of the medium power of the specified range here. The complete assembly to have the measurement of the medium level of the power can be seen in this schematic diagram. So in this schematic diagram, we can start from this point where the input is provided, and in this particular arrangement we have the input load represented, the input temperature gauge. So this is a part of the bridge represented. We have the input headings here. We have the pump that we have to the next part for the comparison load, comparison head, comparison temperature gauge here. So with this arrangement where we have the heat exchanger also, finally we can make the measurement of the medium type of the power here. Now the measurement of the high power here. As we have mentioned, the range of measurement of high power greater than that of the 10 watts. Practically, most possibly we go for 10 watts up to the 50 kilowatts here. So as like for the medium power, what we have, the calorimetric tube, where we had the fluid type inside the tubes here. We have here the calorimetric watt meter of the dry type as well as of the flow type here. So for the calorimetric dry type of the power measurement here, we have a coaxial cable, and this coaxial cable is filled up by the dielectric represented by certain relative dielectric coefficient here, and this is with the high hysteresis loss there. Whereas for the another type where we have the flow type of the calorimetric watt meter, for the flow type we have the circulating water, or instead of water we can also make the use of the oil there, or any type of the liquid which is having the good absorption capacity for the microwave power here. So now in this particular flow type or dry type also we have the measurement with respect to the temperature and the temperature readings correspondingly T1 and T2. So without the device and with the device, or before the device is connected or the microwave power is fed as input, and after it has given it. So the two readings T1 and T2 can lead to the difference of the temperature here. Next to that, the final power can be calculated by using the formulation. The formulation can be given as capital P is equal to capital R in multiplication to K rho here. In the bracket we have the difference of temperature T2 minus T1 here. So this is all divided by the constant value 4.18 here. So in this equation that can be outlined here, we have the capital P, this is the measured power in watts, whereas we have capital R. Capital R is nothing but the rate of flow. This is the rate of flow in terms of centimeter cube per second here, whereas capital K denotes here the specific heat here. The specific heat can be measured in terms of calories per G here, whereas we have rho. Rho is denoting the specific gravity and the measurement unit here, whereas the T2 minus T1 is the difference of temperature in the degree calories here. So for the low power type, the medium power type and the high power type, we have discussed the power measurement techniques here. So for all the types, as it is dependent onto the temperature, whatever the assembly we shall be using for the power measurement may encounter the heat losses there. So some kind of approximations we need to make in the measurement of the power here. So by the next lecture, we shall be introducing the practical power meter, and we shall continue with the same chapter for the different parameters to be measured for microwave test bench here. So I hope you enjoy learning the topics related to microwave engineering. For more such details and the knowledge, you can subscribe to Ekeeda channel. Thank you.